This is the welcome to the next lecture in electronics. This is the part 2 of the electronics. In the part 1 we have discussed the semiconductors. In this series of lecture of electronics, the second part, we are going to discuss the p-n junction diodes. Let us understand that why do we need a diode and some initial thoughts. Let us take the example of a charge circuit operation. In the charge circuit operation, the input voltage is basically the AC voltage. We take the initial voltage example as 110 volt. This may be different for different cases of operation. For here, the example that we are taking is the AC voltage of 110 volt and the frequency being at 60 Hz. So the maximum voltage that the charger input has is 110 root 2, because we know that Vm is equal to Vrms into root 2 and this is the RMS voltage. Then this input voltage is going to step down transformer, and the step down transformer is bringing the level of the voltage to 4 volt. So the maximum voltage now is again AC with the maximum amplitude as 4 root 2 with a frequency of 60 Hz. Because the frequency remains the constant in transformer, whether it is input supply or at the secondary of the transformer. The voltage is brought down from 110 root 2 maximum to 4 root 2 maximum. Now if we consider any black box device that will convert these AC voltage into DC voltage with some magnitude which is less than the DC voltage. So the DC voltage that we are obtaining after passing through low pass filter is 3.5 volt, and this is what the DC is at the output. So in the input we are giving 110 volt AC, and at the output we are getting DC voltage of 3.5 volt, which is possible only when we know this black box device which is able to convert the AC voltage into DC voltage, and that device is known as the diode. So the output of the transformer which using black box, which is a diode here, exhibits a zero DC current content as negative and positive half cycle enclose equal area, leading to a zero average. So you can see that when we have the positive and negative AC cycle of equal areas, then only the positive half cycle we are getting it at the output of the black box. So these may behave as a closed switch and open switch for the first half cycle and the next half cycle of the AC supply. So we can understand from this example of charge circuit operation that why do we need a diode. A diode is needed so that we can transfer the AC voltage or convert the AC voltage into DC voltage, and through a transformer we are basically stepping down the level of the AC voltage. So the basic idea for the diode start from a resistor. So we should know that and comparison of the resistor, that resistor being a linear device. So why do we say the resistor to be a linear device is because the current voltage relationship is a straight line. So if we draw the current voltage relationship, then when we increase the current, the voltage will increase in a straight line. So this is a resistor which is a linear device. Now if we think for a diode, it is basically a non-linear device. It means the current voltage relationship will not be a straight line, rather than it will be something exponential in nature. Then what is the reason? The reason is the barrier potential, which we have discussed in the semiconductor lecture. So in the semiconductor we have discussed that when p-type semiconductor and n-type semiconductor are brought together, then in close vicinity there is some barrier potential being created. So due to this barrier potential, the diode become non-linear. So a p-n junction is known as the semiconductor diode. So semiconductor diode is formed by p-type semiconductor material and n-type semiconductor material when it is brought together. So it is also known as the crystal diode, since it is grown out of the crystal like germanium or silicon, which we have discussed in the semiconductor regarding the formation of crystal. Now diode is also a two-terminal device similar to the resistor, and it conduct only when it is forward biased. Now this is the p-type semiconductor material, this is n-type semiconductor material. These two are joined together and there is a formation of positive and negative, which is the voltage being given. The positive is known as the anode, the negative terminal is known as the cathode, and the symbol of the diode is shown with an arrow, with the arrow head is shown with a bar, and the tail of the arrow is connected to the anode and the head of the arrow is connected to the cathode. So in PN junction, there is the formation of barrier potential at the junction because of the depletion of the charge particle. So the diode conduct only in the forward biased. This also we have discussed in the semiconductor. When the terminal connected with the arrow head is at higher potential, so and the terminal connected to the bar. So here we can see that if it is positive and it is negative, then it is said to be forward biased, and these barrier potential usually is 0.7 volt and 0.3 volt for the semiconductor material. So if the applied voltage is more than this barrier potential, the diode will conduct, and in the reverse bias no conduction will be there for the current. So when the p-type material will be connected to negative and n-type will be connected to positive, then that will be reverse bias condition. So diode do not operate in the reverse bias, diode operate only in the forward bias, and it is a unidirectional device, means the current will flow only in one direction. The current cannot flow in the reverse direction. So diode is a unidirectional device. The reason around the junction where there is no charge carriers, whether it is electrons or holes, it is known as the depletion layer. So here we can see that the connection of the p and n-type semiconductor material where there is no charge carrier, that is the depletion region, and that layer is known as depletion layer. And when potential difference is built up across the p-n junction that restrict the further flow of the charge carrier, that is known as potential barrier. So here whatever the potential is formed due to this depletion region, which is mostly 0.7 volt or 0.3 volt, this is known as the potential barrier. When a PN junction is connected across an electric supply, so here we will be connecting the across the electric supply, the junction is said to be under biasing. So biasing means just to apply the electric potential, whether it is forward biased or whether it is reverse biased. So we can see that if the barrier potential is more than the diode voltage, then the diode current will not flow and it will be less. But when the diode potential is more than the barrier potential, the diode current will start flowing. So these junction where the separation of the charge carrier is there, when the potential is applied, then the diode will start conducting and the diode current will increase. So the diode has to overcome the barrier potential to conduct itself. Now the biasing can be of two types. One is forward biasing and another one is reverse biasing. So what is forward biasing? When the positive terminal of a DC source or a battery, or rather we will tell this one as a source itself, that is a battery or a DC source, whose positive terminal is connected to p-type semiconductor and the negative terminal is connected to n-type semiconductor of a p-n junction, the junction is said to be forward bias. So here we can understand that this will be p-type material and this will be n-type material. So if p-type semiconductor material is connected to the negative terminal and the negative terminal is positive terminal here, and n-type is connected to the negative terminal, then it is said to be forward bias. P stands for positive and n stands for negative. So that we can remember that in the forward bias condition, the p-type semiconductor material is connected to the positive terminal of the battery or the source, the n-type is connected to the negative of the battery. That is said to be forward bias. So the junction barrier potential now will reduce at certain forward voltage, which is 0.3 volt for germanium and 0.7 volt for silicon, and it will be eliminated altogether. So there will be no barrier potential if the applied source voltage is more than the barrier potential. The junction will offer the low resistance to the flow of the current through it. It means when the diode will be forward biased and it will cross the barrier potential, the diode will start conducting. So the diode will start conducting and it will flow the current. The current magnitude through the circuit depends upon the applied forward voltage. How much voltage is applied in the diode, that will decide the magnitude of the current. So in the second category, which we will discuss, what is reverse biasing. So reverse biasing is just the opposite. So in the positive terminal of the source is connected to N-type semiconductor and the negative terminal is connected to P-type semiconductor. That is said to be reverse biasing. And when the reverse biasing is there, the junction barrier potential is strengthened. Here it was reduced. Here in the reverse biasing, the junction barrier potential will strengthen itself. The junction will now offer high resistance to the flow of current. So the low resistance path which was given for the forward biasing has now become high resistance in the reverse biasing case. The current magnitude through the circuit depends upon the applied reverse voltage again. Like what is the reverse voltage is applied, that much current will flow, but in the reverse direction, or in the, we can say this one is a reverse saturation current. We will see what is the reverse saturation current afterwards. So the P-type and N-type semiconductor material are joined now together to form the diode, and we have two terminals. One is known as the anode and another is known as the cathode. The symbol is given with a arrowhead and a bar, and in the circuit if we connect it, so the diode will be connected to the DC source through some internal resistance or external resistance, and the diode will be forward biased and the reverse biased depending upon the polarity of the voltage and the polarity of the P and N type semiconductor. These are the different diode packages that are available in the market with different shapes and sizes which we use for the laboratory purpose. If we see the characteristic of the diode, that is the VI characteristic or the voltage current characteristic, we will be plotting the graph between the forward voltage and the forward current. So the first quadrant is the forward bias region and the third quadrant is basically the reverse bias region. So in the forward bias region, we can see that the nature of this graph is basically non-linear. So it is a non-linear device, and when the barrier potential is increased, the diode start conducting, so which is 0.3 volt or 0.7 volt for the silicon or the germanium diode. And in the third region or the third quadrant, when the negative voltage is applied, then no current will flow and suddenly the saturation current will start flowing. This is known as the knee voltage. So there will be a breakdown of the diode and the current will start flowing in the negative direction. What is an ideal diode? An ideal diode acts like a perfect conductor. Perfect conductor means zero resistance to the path of the current when forward biased. So if the diode is forward biased, then it is a perfect conductor. If the diode is reversed biased, then it is a perfect insulator. Perfect insulator means infinite resistance. That is known as ideal diode. Either it will be perfect conductor in the forward biased or it will be perfect insulator in the reverse bias without having any losses. So here we can see in the diagram for the forward biased, when the diode is connected with the source of the battery and the diode act as a switch. When the switch is closed in the forward direction, the current starts flowing without having any losses. So the VI characteristic, if we see, then the forward voltage and the forward current, the diode will conduct instantly without having any losses. In the reverse bias condition, if we see, when the diode is reversed bias with respect to the supply source, then the diode act as a open switch. So this is open switch and this is a closed switch. So the diode will not conduct, the current will be zero. So this is the ideal characteristic for the diode. Now if we add little bit of offset in the ideal diode, that is the barrier potential, then the barrier potential will be reflecting here. So here the barrier potential is at 0 volt. Here little bit barrier potential will come if we add it in the circuit for the ideal diode. So the diode characteristic curve we can obtain for the real diode condition, ideal diode condition, and a comparison of silicon versus germanium diode. So diode will be on only when the anode voltage is more than cathode voltage. So diode will be on, and if the anode voltage is less than the cathode voltage, diode will be off. And the third category, when the anode voltage and cathode voltage is equal to the diode voltage, then the diode acts as the saturation state. So here in the forward bias region, so in the first quadrant we have the forward bias region for the real diode, and this is for the ideal diode. In the reverse bias region, where you have the knee breakdown or the reverse breakdown, then this is for the real diode and this is for the ideal diode condition. If we compare the silicon versus germanium, so we can see that since silicon is having the barrier potential of 0.7 volt or 0.6 volt, it will conduct a little bit later as compared to germanium diode, which is having 0.3 volt barrier potential. So the nature of the curve remain the same, only the difference is in the barrier potential. So in the forward bias condition, the diode acts as a closed switch, and in the reverse bias condition, the diode acts as an open switch. So above the knee voltage, the diode current increases rapidly. So we can see that when the knee voltage is increased, the diode will conduct rapidly, and a small increase in the diode voltage causes large increase in the diode current. So if we increase the voltage little bit, the current will increase very fast, and there should be upper current level which is given in the dataset. What is bulk resistance? After the barrier potential is overcome, all that impedes the current is the ohmic resistance of the P and N region. So there is some resistance which is offered by the p-type material and the n-type material. So the bulk resistance of the diode is the total resistance offered by the p-type and n-type material. Usually this barrier potential is less than 1 ohm, and the barrier potential depends upon the size of the material forming by P and N region and how heavily doped they are. So usually this is less than 1 ohm. If it is given in the problem, we have to take into consideration, otherwise we can leave the bulk resistance. What is the maximum DC forward current? Now we saw that when the diode is increasing the barrier potential here, then the diode is conducting and current is increasing rapidly. So the diode should have a maximum level of this forward current. So if the current in the diode is too large, what will happen? The excessive heat can destroy the diode. So the maximum forward current rating should be given in the data sheet, which has to be obeyed so that diode do not burn out. The power dissipation in the diode is similar to that of a resistor, where the power equation we can use as the product of the voltage into current. So the diode power is equal to diode voltage into diode current, or the maximum power of a diode is maximum voltage of the diode multiplied with maximum current. So power rating is the maximum power that the diode can safely dissipate without shortening its life or degrading its properties. So due to the current, the heat is produced, and that heat is responsible for the power loss. So that has to overcome, otherwise the life will be short. Now this is the diode approximation chart summary table for the first column, which indicates for a first or the ideal diode. The second column indicates for the practical diode, and the third column is for high level engineering level analysis. So if we see the diode curve for the ideal condition, we can see that it is either the perfect conductor or the perfect insulator. In case of the practical condition, some barrier potential we can add and the diode will conduct instantly. In the high level analysis, it will not be straight line, but it will be exponentially increased. So the equivalent circuit, if we see under the forward biased condition, it will be closed switch. In the reverse biased condition, it will be open switch for the ideal condition. If we take the practical condition, the same condition will be there, but we have to add the barrier potential of 0.7 volt or 0.3 volt depending upon the material. In the high level engineering analysis, we can also add the bulk resistance of the diode to actually calculate what is the current which is flowing in the diode. Like let us take one circuit example. Suppose we are giving 10 volt at the input side and we have idle diode. So at the output we will be getting 10 volt under the forward bias condition. So all the voltage we will get at the output. If we take the barrier potential into account 0.7 volt, then at the output we will get 9.3 volt. If we are taking the bulk resistance also into account, then the practical case will get 9.28 volt into account. So these voltages, whatever we are getting, 10 volt, 9.3 volt and 9.28 volt, depending upon the ideal condition or the practical condition of the diode, that remains very nearby, and hence it doesn't difference answer. But then also, depending upon the condition, we have to opt one of these. What is the diode current equation? So the diode current equation relating the voltage and the current, which is given by this equation, and this equation is exponential in nature, so it is non-linear, where the current I is equal to I naught e to the power v by eta vt minus 1. So here the current I naught is basically the diode reverse saturation current at room temperature, and the voltage V, which is given here, is basically the external voltage which is applied to the diode. The factor eta is a constant, which is 1 for germanium or 2 for silicon, or rather it will be given in the problem depending upon the case to case. So Vt is the thermal voltage which we have to calculate. So thermal voltage is equal to Kt by Q. Here K represent the Boltzmann constant, which is 1.38 into 10 to the power minus 23 joule per Kelvin, and the T represent the temperature in Kelvin, and Q is the charge on the electron, which is 1.6 into 10 to the power minus 19. If we put the Boltzmann constant and charge on the electron, then we can say that the Vt, which is the thermal voltage equivalent here in the diode current equation, is basically equal to T divided by 11600. So we can use this equation directly and substitute the value here to get the diode current equation. So T is in Kelvin, which is equal to degree centigrade plus 273 degree, depending upon whether the temperature is given in centigrade or in Kelvin. Now, if the diode is reverse biased, what will happen? The current equation may be obtained by changing the sign of the applied voltage. So here we will be changing the sign of the voltage because it is a reverse bias condition, and the same equation we can use it for the reverse bias condition. Now, if the supply voltage is very greater than the thermal voltage, then the term e to the power minus v by eta vt will be very less than 1, and hence we can say that I will be approximately equal to minus of I naught. That is the reverse saturation current, which is valid as long as the external voltage is below the breakdown value. So when we are applying the reverse voltage, this one negative, then the reverse saturation current I naught will be flowing. This reverse saturation current will be flowing as long as there is a breakdown because of the voltage magnitude in the negative direction. The next topic that we are going to take is basically the load line. So load line is an efficient tool to find the exact value of the diode current and the voltage. And the equation we can use from the Ohm's law is the diode current is equal to the supply voltage minus the diode potential divided by the total resistance in the network. Now here let us take one example. If the supply voltage is basically 2 volt and the resistance offered by the circuit is 100 ohm, then we can have two different cases. Like case 1, if the diode voltage is 0, if we set this one as 0 volt and the resistance here it is 100 ohm and the Vs value is 2 volt, what will be the diode current? The diode current will be 20 milliampere. In the second case, if we set the diode current to be 0 ampere and the Vs is equal to 2 volt and Vd is also 2 volt, that is possible under this case only. Then we can draw in terms of the curve of the diode voltage and the diode current curve. So the diode curve what we are obtaining because of the voltage Vd and the current Id. Now the two cases that we have taken, case number 1 and case number 2, where the diode voltage was 0 and the diode current was 0 when the diode current is 20 milliampere. So diode voltage is 0 when the diode current is 20 milliampere. It means if we see that when the diode current is 20 milliampere here, then the diode current is diode voltage is 0, and when the diode current is 0 only when we are getting the diode voltage as 2 volt. So these 2 points are very important point for obtaining a straight line which is known as the load line. We know that if we get 2 points we can draw a line. So the 2 points are basically the saturation point. Why saturation? Because no more current is increasing. And the second point is the cutoff point. Why cutoff? Because the current is not there and voltage is also not there. And the point where it is intersecting the main diode curve, that point is known as the quiescent point or the point at rest, and these will be the operating point. So the straight line which is obtained by intersecting the cutoff point and the saturation point, when it is intersecting the actual diode curve, that point is known as the operating point, and the corresponding current, that is 12.5 milliampere in this case and 0.75 volt in this case, are actually the operating point and the operating voltage. So operating voltage and operating current is the point which we are getting once intersecting the diode curve with the load line. So the load line is basically very important tool in experimental purpose. Let us see the first problem in this particular topic. So if we have a germanium PN junction diode which is forward biased with a voltage of 0.7 volt applied across it, the diode has a saturation current of 10 microampere and the forward bias resistance is 50 ohm. Calculate the current flowing through the diode if the thermal voltage is 26 millivolt. So the given condition, we have the forward bias voltage 0.7 volt, the saturation current is given to be 10 microampere, and the resistance, forward resistance, which is equal to 50 ohms given. The ideality factor we can take 1 because it is a germanium diode, and thermal voltage is also given 26 millivolt. The equation of the diode current is given I equal to Is, that is the reverse saturation current, e to the power the supply voltage V by eta Vt minus 1. So all the data whatever is given may be substituted in the diode equation and we will get the diode current as 0.205 amps. So in this problem we can easily obtain the diode equation using the given data. Now what is the diode operating as a rectifier? So we can understand that if the AC voltage is converted to DC voltage, this is known as rectification, and the device which is used for converting AC to DC is known as rectifiers. And when the inverse process is being taken place, that is DC to AC conversion, that is known as inversion. So if it is inversion, then obviously the device which will be used is known as inverter. So AC to DC conversion required a rectifier and DC to AC conversion required inverter. So we will focus on rectifier here because we are studying the diode as a rectifier. Now why the AC to DC conversion is required? So when we think for electric power generation, transmission or distribution, everything are AC for economical reason. We know that when power is generated, transmitted or distributed as a high level of voltage, then the losses is reduced. Hence for economical reason AC is preferred over the DC. The alternating voltage is available at the main supply, but most of the electronic circuit need DC voltage for their operation. So electronic circuit, obviously we require a DC voltage, but the mains is basically alternating in nature, and hence the rectifier is needed to convert the AC to DC. We require AC to DC conversion so that we can use that in electronic circuit. So the rectifier can be of two types. First is the half wave rectifier and the second is the full wave rectifier. So from the name itself we can understand what is a half wave and a full wave rectifier. because the AC half cycle has two wave. One is the positive and another is negative. So two cycle it is, of full one cycle with two waveform. So if one of the cycle is rectified, that is known as half wave rectifier. If both the cycle is rectified, then that is known as full wave rectifier. Let us see the half wave rectifier first. So half wave rectifier is a simple electronic circuit that convert alternating input signal into a pulsating DC output signal, and it uses a diode as its main component. So the application of a diode is to make the rectifier circuit, and first we will study the half wave rectifier, which will convert only one half of the AC signal using the diode. So what is the operation? So the AC input signal is applied to the primary side of a step down transformer. So we have seen from the initial thought only we will require a transformer, and the primary of the transformer will be supplied with the AC voltage, and this is what the AC voltage we are supplying to the primary side of the transformer, and the diode will be connected to the secondary side of the transformer, and this is basically step down transformer. So the transformed AC voltage is then applied to the diode, which act as a one-way valve for the electric current. So diode, which is basically unidirectional device, it is basically one-way valve. So current will flow only when it is forward bias in one direction. It cannot flow in the reverse direction. So during the positive half cycle of the AC input, the diode conducts and allows the current to flow through it, resulting in a positive voltage across the load resistor. So if we take the positive half cycle, then there the diode will be conducting and the current will start flowing, so there will be voltage across the load. So you will get the voltage across the load terminal, and the negative half cycle of the AC input cycle will be reverse bias. So hence no current will be flowing, because we know that under the reverse bias condition no current flows, and the diode act as a reverse bias, and no voltage will be present in the load resistor. The output waveform of the rectifier is basically a pulsating DC voltage that only contains the positive half cycle of the input signal. So we are getting only positive half cycle of the input signal at the output. Now here we can understand this is the transformer primary, which is connected with the AC input. The secondary of the transformer, this is a step down transformer, is connected to the diode and the load resistor. So the output whatever we are getting is pulsating DC output only for the positive wave. The negative wave we are not getting at the output. So this circuit can be represented with a simple single phase equivalent circuit where the input voltage is V sin omega t, there is a diode, and we have a load resistor. So when the diode is forward biased, then diode act as closed switch and the current start flowing, so we'll get the output voltage. When the diode is reverse bias, then this is open switch and no current will flow, so the output voltage also will be zero. As such, for the input AC voltage, we will be getting that pulsating DC voltage only for the positive half cycle of the AC waveform. So the negative half cycle we are not getting, and this is what the half wave rectifier principle, where only one half of the AC wave we are getting at the output. Now the important formulas that we can use for the half wave rectifier, that the peak voltage we know that is Vm by root 2, because we are writing the equation of the input supply as Vm sin omega t. So V of t is equal to Vm sin omega t, that is what we are applying to the diode, and the peak voltage is Vm by root 2. Average voltage is given by V peak by pi. So from here we put it here and then divide with pi to get the average voltage. Peak to peak voltage. So what is the meaning of peak to peak voltage? Now here you have a AC cycle. So this is what the peak voltage we have Vp, and here we have the negative Vp. So this is peak to peak voltage. So that is twice the peak voltage. RMS voltage is Vp by root 2, and the rectification efficiency is output voltage by RMS voltage into 100, or otherwise we can say that output power by input power into 100 will give you the rectification efficiency. In the full wave rectifier we use, because the half wave rectifier there is a significant power lost. So full wave rectifier generally provide a smooth and steady supply of power. A full wave rectifier converts the complete cycle of alternating current into pulsating DC. So both the half cycle will be rectified now in a full wave rectifier. Full wave rectifier utilize the full cycle of the AC input, so the loss will be reduced. And there are two methods to convert the full wave rectifier. One is known as the center tap rectifier and second is known as the bridge rectifier. In the center tap rectifier, we use a center tap transformer and two diodes. So we use two diodes in the center tap rectifier. In the bridge rectifier, we use standard transformer with four diodes for arranged in the form of a bridge. So these are the two different ways of full wave rectifier to get both the half cycle rectified. So let us see the center tap full wave rectifier. In the center tap full wave rectifier, we have a transformer whose center is tapped or grounded, and the input of the primary is given with the AC voltage, and there is two diode connected to in the circuit. So secondary is connected with two diodes D1 and D2. So positive half cycle D1 will conduct and the negative half cycle D2 will conduct, and hence we will be getting both the half cycle rectified. So full rectification will be there. So center tap transformer, which is a step down, and two diodes are required in the full wave rectifier, and the output voltage is obtained across the load resistor. So here the output voltage will be obtained. Now note here, this load resistor is connected with one of the terminal and the center tap. So the step down transformer convert the high voltage AC into the low voltage AC. So we have to reduce the level of the voltage using step down transformer. Positive half cycle of the AC input, only one diode, that is D1, will conduct. It will act short circuit, and D2 will act as an open circuit. So in the negative half cycle, the reverse process will occur. D1 will become open circuit and D2 will become short circuit, and hence both the half cycle we will be getting. So DC voltage is obtained for both positive and the negative half cycle. So here both, with the use of the two diodes, positive and negative half cycles, we are able to rectify. Now in the bridge rectifier, we are having four diodes. So D1, D2, D3 and D4. So the AC input is applied at the input side, and through the load resistor we are getting the DC out. So in the forward biased, or in the positive half cycle, what is happening? So if you take the positive half cycle, so the diode D1 and diode D3 will conduct. So the current will flow in this way, whereas the diode D2 and D4 will be off or reverse biased. In the reverse bias condition or the negative half cycle, so positive half cycle we have applied where the diode D1 and diode D3 conducts. In the negative half cycle, so in the negative half cycle we see the current will flow in this direction. So it is the D4 and D2 which is conducting now, or become forward biased, where D1 and D3 are reverse biased. So the input AC cycle, which is the positive half and the negative half, both are getting rectified and getting a full DC output in the pulsating form. After this we can have filter connected to get the constant DC voltage. So after this step we will have the filters connected. So the important formulas relating the full wave rectifier, where we need to find what is the peak inverse voltage. So peak inverse voltage we need to find for both half wave as well as full wave rectifier. So definition of peak inverse voltage is what is the maximum voltage that the diode can withstand in the reverse bias direction. So when we have the AC input positive and negative, this is forward biasing condition and this is reverse bias condition. So in the reverse bias condition, the negative maximum is basically the peak inverse voltage for the half wave rectifier. So in the full wave rectifier, that will be double of the half wave rectifier. So that will be 2 times the Vmax. So here whatever the Vmax will be there with a negative, That will be twice in case of peak inverse voltage for the full wave rectifier. In the half wave rectifier, it will be only Vmax. And the output DC voltage will be I average into RL, which is I mean into RL, and I average can be written as 2 by pi I max into RL. I RMS, we can find I max by root 2. Rectification efficiency is basically the DC output power by AC output power. So if we consider the entire system to be a black box, here the input we are giving as AC and the output we are getting DC. So this is output is DC and the input is AC to obtain the efficiency. What are ripples in rectified DC output? Ripples refer to the small fluctuations in the output voltage or the current of a rectified circuit. So whatever the fluctuations we are getting in the voltage and the current for the rectification, that is known as ripples. It is caused by the pulsating nature of the rectified waveform. So the rectified waveform is pulsating in nature, and this consists of the positive and negative half cycle. So during the transition between the half cycle, there is a brief period where the voltage or current decreases and crosses zero, and hence the transition period lead to fluctuation in the output, resulting in a ripple formation superimposed on the DC signal. So ripple is typically expressed as peak to peak value or the RMS value of the fluctuation, and it is undesirable in the application because we require a steady and a smooth DC voltage or a current. Ripple can cause distortion, malfunctioning in the sensitive electronic equipment. Hence, we require to put filtering or regulating technique so that we obtain a stable DC output. So ripples are basically the fluctuations which causes losses, and through filtering and regulating technique we can control it in the output DC voltage. So let us see the summary of the half wave rectifier and the full wave rectifier. The full wave rectifier can be center tapped as well as the bridge rectifier. So the number of diodes, if you see in the half wave rectifier we are using 1, and the full wave rectifier for center tapped we are using 2, and for bridge we are using 4. The DC voltage that we are getting is Vm by pi in half wave. Here we are getting 2 Vm by pi and 2 Vm by pi for both the center tap and bridge rectifier. The RMS voltage is Vm by 2. Note here we are not dividing with root 2, but in the full wave rectifier we are dividing with root 2. Ripple factor is 1.21 for half wave rectifier, which is more as compared to the 0.482 in case of full wave rectifier. Rectification efficiency, if we take the maximum, in case of a full wave it is 81.2%, but in case of half wave it is 40.6%. So whenever we are solving the numerical, we have to see if the efficiency falls for the half wave close to 40%, then the answer will be correct. If it is fall close to 81%, then the answer will be correct for full wave rectifier. The load current maximum is Vm by Rf plus RL, which is 2 RF in case of the bridge rectifier. So the peak inverse voltage, we have seen that 2 Vm will be the case for the center tap, but Vm in case of half wave and bridge rectifier. Ripple frequency is twice again for the center tap and the bridge rectifier, but in the half wave rectifier it is only F. Let us solve a few problems to understand the rectification principle that we have studied now. So here the first problem, we have an AC supply of 230 volt. So we are giving 230 volt. Note here whatever the voltage is mentioned, that is always the RMS voltage for the AC. This is applied to the primary of the transformer, and the transformer is basically 10:1 transformer. So it is a step down transformer. We have to obtain the output DC voltage, peak inverse voltage, assuming that the diode is said to be real. So here we are having 230 volt. So the maximum voltage is 230 root 2, that is 325.3 in the primary of the transformer, and the secondary of the transformer we can get from the transformation ratio N2 by N1, and here in the secondary side we will get the voltage 32.53. Note here, this we are calculating from the maximum side. We can calculate this directly from 230 volt because we know the relationship V2 by V1 is equal to N2 by N1. So directly we can substitute the RMS voltage to get the RMS V2 first and then multiplied with root 2, you will be getting the maximum voltage. So either you can move from this step or you can move from this step. Both will give the same answer, close approximation. Now here in the load resistor, what is the voltage which is obtained? So the current which is moving here is IDC. So IDC into RL will be VDC, Ohm's law. And we know that for a half wave rectifier, because this is half wave, only one diode is there. So Im by pi is the IDC. And since the voltage is mentioned on the secondary side, so I will be converting Im into RL is equal to VSM divided by pi. So pi is a constant here, and hence we'll substitute VSM as 32.53 by pi, we'll get 10.36 volt as the DC voltage. The peak inverse voltage is basically the reverse voltage. So we can see that the negative half cycle, which is having the maximum magnitude of 32.53, that will be the peak inverse voltage. Next problem, here we have a crystal diode whose internal resistance is given to be 20 ohms and it is used as half wave rectification. The applied voltage is 50 sine omega t and the load resistor is 800 ohms. We have to obtain the maximum current, DC current and the RMS current. We have to obtain the AC power input, DC power output, the DC output voltage and the efficiency of the rectification. So from the given voltage equation 50 sine omega t, we can say that the maximum voltage is basically 50 volt. So the current which is flowing maximum is basically the maximum voltage divided by the total R equivalent, which is equal to RF plus RL. That gives to be 61 milliampere as the current, maximum current. The DC current we know for a half wave rectifier is Im by pi. So we'll get 19.4 milliamp, and the RMS current will be Im by 2. Note here we are dividing with 2 and not with root 2. So that is 30.5 milliampere. The AC power input from the Ohm's law is I RMS square into RF plus RL. Now note here, this is what we have the transformer. So there is some internal resistance RF and the load resistor RL. So this AC cycle is both for RF and RL. So we are taking RF plus RL both when the current IRMS is flowing. So that is equal to 0.763 watt. Whereas for the DC power output, now if you have a diode here and the load resistor is connected here, RL. So here we do not take RF into account, only RL, because the DC current is losing its power in the load resistor. So that will give 0.301 watt. DC output voltage will be IDC into RL. So here we have the load resistor RL and the voltage across it we have to find. So what is the current flowing? That is IDC. So IDC into RL will give you the DC output voltage, which is 15.52 volt. And the efficiency is basically the output power by the input power. Input power will be AC, that is 0.763, and the efficiency is 39.5, which is close to 40% in case of half wave rectifier. So our answer will be correct because it has to be close to 40% for the half wave rectifier. Now if we have a half wave rectifier which is supplying 50 volt DC to a resistive load of 800 ohms, the diode has a resistance of 25 ohms. Calculate the AC voltage required. How much AC voltage is required by the diode. So these are the given datas for the problem VDC, RF and RL. So we know that VDC is equal to IDC into RL, and if the maximum voltage is Vm in the given condition, then IDC is equal to Im by pi, and Im can be written as Vm by RF plus RL. So obviously we are going to get one equation of VDC as this one. So this is VDC, and the unknown quantity here is Vm. So Vm comes to be 162 volt. Now the fourth problem is based on full wave rectifier, and it is said to be 2 diodes, and we know that 2 diodes are used for center tap transformer. The internal resistance of each diode is constant at 20 ohms, and the transformer RMS secondary voltage from center tap to each end of the secondary is 50 volt. So this is the secondary voltage which is center tapped. The load is 980 ohms. We have to obtain the mean or the average load current and the RMS value of the load current. So the given data is the internal resistance and the load resistance, maximum AC voltage. So this 50 volt is the RMS voltage. We have to compute everything in terms of the maximum. So we are converting that to maximum voltage 50 root 2, and the current is basically Vm by Rf plus RL. So that is equal to 70.7 milliampere. And IDC is equal to 2 Im by pi. Note this 2 is coming because it is a full wave rectifier. So that is 45 milliamps. IRMS is Im by root 2. Note here we are dividing with root 2 and not with 2. That is in case of half wave rectifier. So it is 50 milliamps. Next problem. Here we have a center tap circuit. The diodes are assumed to be idle. No losses will be there and no internal resistance will be there. You have to obtain the DC output voltage, the peak inversion voltage, and the rectification efficiency. So the input is having 230 volt. This is the RMS voltage. The step down transformer ratio is 5:1. The center tapping we have here, and the diode is idle. Output load resistor is basically 100 ohms. So the given data whatever we have and what we can calculate. So 230 volt input with a 5:1 transformer. So 46 volt we will be getting at the secondary. And these 46 multiplied with root 2, we will get the secondary voltage maximum, which is 65 volt. Now we have to get the center tapping. So 65 volt divided by 2, we will get 32.5 volt as the maximum voltage. And IDC is equal to 2 Vm by pi RL. So IDC is 0.207 for the full wave rectifier. Peak inverse voltage is nothing but the total secondary voltage whatever we have. So that is 65 volt in this particular case. Now IRMS is Im by root 2, which we can write Vm by root 2 into RL, that is given 0.229 amps. And the rectification efficiency is output power IDC whole square into RL by input power IRMS square into RL, which comes to be 81.7%. Note here again that this is close to 82%, and we know that for a full wave rectifier the maximum efficiency is close to 82%, which is quietly true for this case. So this complete the second part of the fundamental of electronics for the first year EEE program, and we have complete PN junction diode. Next we will be taking the bipolar junction transistor, and that will be the end of the fundamental of electronics. Thank you for now. See you in the next lecture.